Welcome back. So much like the real world, where we have tons and tons of varieties, types of trees, we've got different categories of trees, we've got families. I'm not a botanist. I do like trees though, but there are many, many types, and we can enjoy them all out in the world. Anyway, in the world of computer science, the data structure of the tree, there are many varieties as well. So actually on Wikipedia, there's an article that contains a list. I don't know if it's complete, but this, from here on out, I'm going to scroll through. These are all varieties of trees, all different types. So they all follow the same rule defined by, like, they fit the pattern of a tree, but they all add in some special properties, some rules, basically something that makes them a bit different. And often, some of them will be much faster at searching or insertion of a particular thing, or they excel at storing data in a particular format, or data that is, contains a lot of duplicates, or data that's all unique. They all, I haven't heard of the majority is not even a good way of putting it. I haven't heard of like 95% of these. There's some very niche trees here. And you can see also there are different categories of trees, like heaps. Oh dear, I don't know if you can hear that. My cat's, hang on. Hey, come on girls, what are you doing? Sorry about that. Where was I? There are many types of trees in different categories, different groupings, like heaps, which we'll learn about later. What we're going to talk about in this video, mainly, are binary trees. So one group, sort of like you could think of in geometry. There's this thing called a polygon, just any shape. Well, I guess not any shape, any sided shape where there's n number of sides. And within that, we have quadrilaterals. That's one family, just like this is a family. And then we have triangles, another family. And within that, we could have, within quadrilaterals, there's rectangles and trapezoids. And that's about as far as my geometry goes at this point. So the trees that we're going to focus on are trees in general. We've already kind of laid that out. But more specifically, binary trees. And even more specifically, binary search trees. So binary search trees are a special type of a binary tree, which is a special type of a tree. And they excel, as you can imagine from the title, at searching. So we store sorted data in a particular way, we'll get there in just a moment, in a binary search tree, which makes it easier to retrieve. Let's just recap. This is just a generic tree. Each node could have any number of child nodes. We've got, this one has 4 children, 1, 2, 3, 4. This one has 0 children. This one has 3. This one has 2. This one has 1. There's no real rules about how many. A binary tree, on the other hand, has a special condition. Each node can have at most 2 children. That's the binary part. So it could have 0 children, can have 1 child, and it can have 2 children. So our root node usually would have 2, and then each node could have 2, or it could have 1, or it could have 0. But it can't have 3, for example. This is not a binary tree. This is a valid tree in general, if we're just talking about a generic tree, but it is not a binary tree. And there are also, I've heard of ternary trees where there's 3, at most each node can have 3 children. I'm sure there are terms for, quadrinary, I don't know, 5, 6, 7, 8, but they're just not as commonly talked about because binary trees have some special properties that make them easier to navigate. And we'll talk about that when we talk about binary search trees, which is actually right now. So binary search trees are a special case of a binary tree, which is its type of a tree. So they are trees. They, at most, have 2 children per node, 0, 1, or 2 children. And on top of that, binary search trees are sorted in a particular way. They are kept in an order. So BSTs, which is what I'll probably say most of the time because binary search tree gets a little bit annoying to say. BSTs are used to store data that can be compared, that is sortable. So often, classically, we're talking about numbers, and that's what we'll be working with. It could be strings. It could be any other piece of data that has some way of, there's a way for you to order it and compare things. Which one is greater? Which one is less? So this is how they work. This is the special magic property. If we take any node on the tree, let's try the root, all numbers or every item that is less than this node is located to the left of it. Every item or number in our case that is greater than is located to the right. And you could repeat that on each child node. So if we look at 6, to the left are the numbers smaller than 6. To the right are the numbers greater than 6, like 8. Or 15 over here, we only have one node, but 20 is greater than 15, so it's located to the right of it. So to review that, A binary search tree is a type of a binary tree. Every parent node has at most 2 children, but on top of that, every node to the left of a parent node is always less than the parent, and every node to the right of a parent node is always greater than the parent. So here's a slightly larger example. We take any node, like the root, all nodes to the left, all of these should be less than 41, and everything to the right is greater than 41. And then we could try that again over here at 20. Everything to the left needs to be less than 20, and it is. Everything to the right is greater than 20. Same thing down to 11, blah, blah, blah. Over here, it's the same exact property. So that's what makes a binary search tree rather than just a binary tree. So that the data is kept in a particular order. Every node, every child to the right is greater than a parent node, and every piece of data to the left is less than the parent node.